Hi, this is Dan. I'm going to go through the practice exam over Unit 1. Obviously, there might be some different ones than what you see here because the questions are scrambled or pooled. So I would suggest going through the exam, at least 2 or 3 times so you can kind of get a feel for all the different types of problems. I may chunk this video out as well based on how long it's getting. So I'm just going to go through just as they're coming to me, show how to do them. I will show at least one of the show work problems, and then after that I might just let that go just to save a little time because I'm trying to explain on top. But anyway, so we've got in this one, in question 1, we've got 6 flights from Las Vegas to Newark. I compute the range and sample standard deviation of flight time. So you just open this in StatCrunch and just do some summary stats on it. It should give us everything we need. So let's go. And if you want, you can split screen StatCrunch like that, and then like that. So that's maybe a way you can take the exam to keep StatCrunch open. Anyway, so if you just go stat, summary stats, columns, and there's one variable stats. I just do the default. So the range is 25. That's the difference between the highest and the lowest. And the standard deviation is it says round to integer or decimal or 1 decimal place, so that'll be 9.0. So let's go 9.0. And I think that's all I wanted. All right. Let's go on number 2 here. Recently, a random sample of 25 to 34-year-olds. How much do you currently have in savings? And they got that in a table. They want the mean and sample standard deviation. Again, this is very straightforward. This is in a frequency distribution, so this is a little more interesting. And we had one like this from our homework too, so this would be a good one to go through. So I want to find the mean and standard deviation essentially of this distribution. Since we don't have the raw data, we just know there's 335 scores in that range. So we can do it a couple different ways. We can say we have 335 scores that are in the middle of that range or the midpoint between the classes. So I'm just going to go stat, and we're going to go tables, or I'm sorry, yep, there we go, stat, yeah, stat, summary stats, there we go, grouped bin data, sorry. So the bins are in the savings and the counts are in the frequency. And you can pick the midpoint on the limits of the interval or the consecutive lower limits. I'm just going to do this first one, the default, and see if it likes that one. So I'm just going to compute there. All right, and so we've got that. So the sample mean is, let's see, around the nearest dollar. So it'd be 236. So that's probably, it'd probably be fine with either one, I have a feeling, because they're not making it be super accurate. Maybe not. Standard deviation, and that is rounded to the nearest dollar as well. So 228. Let's see, like that. 228. Let's check that. All right, looks good. Cool. All right, we'll go into number 3 here. Non-sampling error is when the error occurs are not used to estimate, and sampling error is when the results are used to explain. Yes, there we go. So non-sampling refers to error that results from the process of obtaining the data, and sampling error is that occurs the results from the sample are used to estimate a parameter from the population. So this is one of those definition kind of ones, kind of wonky. I'm assuming you did them in your homework as well. So non-sampling, that's just based on the process that you're essentially missing data that you should get. You get error from that. And sampling error is when they're used to estimate a parameter. So essentially that would be a misuse of inference, would be a better way to explain that to me. But we haven't even gotten to that yet. But anyway, it's kind of a wonky question, I would say. So, all right, let's go on to number 4 here. Determine whether the quantitative variable is discrete or continuous. Discrete means it's countable. Continuous means it's a continuous phenomenon. There's nothing skipped. So it's the number of hands folded by a player. You can definitely count that. So it's going to be discrete because it is countable. All right, where like water filling in a pool would be a continuous phenomenon, because you can't say it because it doesn't like skip to a discrete. It means like 1, 2, 3, like counting people or cars. All right, let's go in here. This is number. Where's this? Number 5. Oh, and this is a show work question. They're going to have us do a stem and leaf plot, and then we're going to take a picture of that and put it in there. So I'll show all of those steps. All right, so we click the data, and if we just open this in StatCrunch, and then it wants to do a stem and leaf plot. So if we go graph, stem and leaf, var1, and if I just leave it default, let's see what it does. It looks like it does split it into 5s, right? Just like kind of like what we're seeing over here in our examples. So I'm going to try to do a little split screen here. Let's see if I can do that. Recording. There we go. And then we'll go here, and I'll close that. All right, get over this later. So let's see here. The one that looks most like it looks definitely like A. And then it says, describe the shape of the distribution. So we can see it looks like it's, honestly, it's pretty symmetric. One mound is unimodal. So let's see here. I would say it's bell-shaped. Yeah, for sure. It's unimodal and mound in the middle, so it's not skewed. So I'll hit, and then for show work, you want to have a picture of this. So the way I do it is I use Snippings tool. So I'm just going to go to Snippings tool or whatever you use in your Mac to take a little screenshot, and I hit new. And I'm just going to go ahead and just drag a box around that. And that's what the work I'm going to want to submit. I'm going to go ahead and save as, and I'll just put it on my desktop for now. And I'll call it stem and leaf. Desktop. There we go. And then I can go over here and click the little image icon and go to my desktop. And there's my stem and leaf. Hopefully it likes that. There it is. So I've got that saved, and it should say that. And I check my answer. Oops, looks like I made a mistake. Which one did I miss? Did I make a mistake? Did I pick the wrong one? Maybe. Did I make, let's see, 5, 6, 7, 8, 9, 9. Those all look right. Those all look right. Those all look right. Okay. So I'm trying to think what's the I'm trying to see the difference between these two right here, because they're looking pretty similar. Wow. Boy, those look identical. Okay. I'm not sure why. What's the difference between these two? I don't even see any difference. It looks just like what I'm supposed to have. Boy, what if that's a glitch? Because I think 1, 2, 3, 4, 1, 2, yeah, I think looks, yeah. Well, that's not good, because both of those are the same answer. Oh, maybe not. Here it is. There, I found one little error. Oh my goodness, it's that. Look at that. 5, 0, 5, 1. It's that. Oh my goodness. So I guess be very careful about that. That's not cool. But anyway, it's good that we're going through this now, so you know. All right, let's move on. And there we go. A blank experiment is one in which neither the subject nor the researchers know which treatment is. So this blinding, single blind is like the people being examined and don't know, or the researchers don't know. If they both don't know, it's what we call a double blind study. All right. Here's a question that we had in our homework, and it's just trying to randomly select 4 out of a group of 32 names. So if you click this names, you can load that StatCrunch, but there's not a huge need, I guess. And we can open StatCrunch since we're using StatCrunch. So it'll put them in a list, and we just have to figure out how to randomly select those. Now, according to this methodology, it's going to want us to go data, simulate discrete uniform, the same, 10 rows, 1 column, min and max. I'm just going to go ahead and pull that up. So I'm just going to put this at half. Wrong half. There we go. Put this at the other half. Okay. So if we go to data, simulate discrete uniform, 10 rows, 1 column, minimum is 1, and the max is, since there's 32 names, it's 32. And we got to make sure we put in a fixed seed here, and they're saying it's 1, 2, 6, 5, 2. And compute. So it gives us 10 numbers, and you have to find the first 4 that are not repeated. So looks like 5, no repeats, 28, no repeats, 24, no repeats, and 32. So that would be Cooper, and 28 is Thompson, and 24 is Redmond. Let's see what's on here. I think I mischecked. I don't want to check that. There we go. Redmond, Cooper, Zinkel, and Thompson. Another way you can do this that I think is actually way better is just to use the applet to select random numbers and use the same seed, and you'll get the same answer. So I'll just do that really quick to show this. I would rather go applets, random numbers. I just want 0 to 32. I want 4 of them, and I use the same fixed seed, 52, and hit compute. And there you go, we get the same 4 numbers. So the other one, you have to be careful if there's repeats and all that stuff. This would just do it, but again, it's the same 4. So that's how you do that one. So I'm going to kind of go through a few of these again. What is a frame? It's essentially all the individuals in a population that are being studied. So it's anybody who's capable of being in the study from the population, because the sample comes from a population. Let's see here, next one. The blank is the difference between consecutive lower class to the class width. So we had a homework problem that was like with the value, or how much disposable income is like 30,000 with a width of 6,000. So if you go from 30,000, the beginning of the next interval is 36,000. That's called the class width. All right, on this one, researchers wanted to determine if there was an association between daily tea consumption and the occurrence of skin cancer. So they looked at a whole bunch of women and asked them to report their tea drinking habits. They were also determined which women had non-melanoma skin cancer. After analysis, researchers concluded the consumption of 6 or more cups of green tea per day was associated with a reduction in skin cancer. So this is definitely an observational study, because they didn't manipulate a variable. They just observed women and just kind of said, what kind of tea behaviors do you have? And it says this is a cross-sectional one because it was all at the same specific time. So they checked them all at the same stage, I guess. If they were at different stages, it might be a longitudinal study. But what's the response variable? It's whether they had skin cancer or not, and that is a qualitative analysis. The explanatory variable is if the green tea is causing it, which is funny. And then in the report, after adjusting for various demographic and lifestyle variables, daily consumption was associated with a 30% reduction prevalence of melanoma skin cancer. Why is it important to adjust these variables? So what they're trying to do there is control, right? So we're going to look at people that have the same in these different things, like they have the same life daily, So if it was, they looked at the ones that just to eliminate those as potential lurking variables, then they did see something. So it tries to isolate that variable from within their observations. So they call them confounding variables. So we're trying to reduce the amount of things that could explain why that's the case. It can be socioeconomic status or job or education or marital status or all these things. they're trying to say, okay, what if we control for those? What if that we look at groups that all have those in common? Do we still see, when they have this very high amount of tea consumption, do we see a difference? So that's a good question. All right, here's another one. Determine whether the underlying values of parameter statistics. Remember, parameters are something that describe the population. A statistic describes a sample. So, the following election, 18% of the governors of all 50 states of a country were female. Obviously, it's describing all of the governors, so it would be a parameter because the 50 governors are the population. All right, let's go to the next one. The following is an ogive, or standardized test scores. The vertical axis in an ogive is the cumulative relative frequency, and it can also be interpreted as a percentile. Okay, so if you look at it, it's almost like a normal distribution, really bit. So like there was a 70 is the 0th. Nobody, that's like the lowest score, and then only a few percent got 90s, and then you can see 20% scored 110 or below that we've got. So that's why you can use them as percentile ranks, and then everybody. So it says interpret the rank with value of 120. So if you go to 120 here, and you can see right there, that's essentially the middle, or the 50th percentile. So it's the 50th percentile of the tests, and 50. So that means half are that or less. 130 right here would be the 80th percentile, and then what would be which score is the 20th percentile? That would be 110. So I'm trying to teach you how to just read that. It's kind of like just the percentile rank. Determine whether the quantitative variable is discrete or continuous. Again, discrete, it is, you can count it, and continuous is you can't go like 1, 2, 3. So it's definitely, snowfall is a continuous event. It's not like they're skipping levels of snow as it's snowing. So it's not all, kind of like your height is continuous as well. All right, so we've got some data here. I think I already did this one earlier because they're pooled up. But again, you just open this in StatCrunch and do summary stats, and hopefully that's part of the early part of this video. I'm sorry. And then to find the outlier, actually, I'm just going to do this one. Let's go ahead and do it again. Open in StatCrunch and just do summary stats. So you just go summary stats, columns. So variable 1. So that gives us all of the relevant things. It gives us the first quartile, the median, the third quartile, and the max, and then that's how you get all these percentages and those values. And then if there's an outlier, StatCrunch can do that for us as well. And the easiest way is just to have it do a box plot. So just go to graph, and then go to box plot, and just do var1. And I like to draw them horizontally just so it's easier to see, but there you go. So you can see there's one data point. I put my mouse on there. It's like there it is. It's 44. So there's one outlier, and it's 44. So it kind of gives that to you. So again, the median was 10. That's the 50th percentile. 6.5 was quartile 1. That's 25th percentile. It's kind of interesting. They say 25% or below, which means there's 75% above. Duh. Median 50% below, 50% above. Third quartile, 75% below, 25% above. So that's pretty straightforward there. But I thought the little hack there is to make a box plot to find the outlier. And the box plot will actually give you all those other values too if you just do the graph. So that's another way to do it. Here. All right, this is another example of a show work problem. I think I showed that already earlier, but they want to find an appropriate graph. It says consider appropriate graphs for these using one that you think is best. So this is not just one answer here, and then you can show your work. Justify your choice, explain why your graph was chosen. And you can write that on paper, or you can type it in. And there is a spot online that you can submit work from written work, or you can just type it in. So if we go to the show work thing, oh, I ever hit the show completed button, so it won't let me do that. So you could actually type it in there or write in there if you want. Either way is fine. So I'm just go ahead and open this in StatCrunch. There's lots of different ways you could show that and just represent. So it's nice to see the distribution. So I really like histograms for ones like this. So if I just do that, and I'll just do the default, kind of gives the histogram, the shape of the distribution. That would be fine. You could do a frequency with intervals, but yeah, I think histogram is the best when you're trying to look at the shape of a distribution. And you can say, yeah, just right. Why did you explain that? Because I think the histogram shows the shape of the distribution. And then it says, oh, summarize the distribution in a sentence or two. So I'll go ahead and do that again. Open StatCrunch. I'll make my histogram quick again. Sorry about that. Graph, histogram, R1, compute. So you could say there's definitely, looks like there's one that's maybe an outlier here, but it definitely looks like it's unimodal, right? Unimodal. This data point may make it a little skewed left, but you know, if you took that one out, it would definitely be a little skewed to the right because it tails that way. So really, I'm just saying, you know, unimodal, maybe with an outlier, something to that effect would be just fine for that description. And you can type that or write that out and submit it. Another one. Often the frequency distributions are reported with unequal class widths because the frequencies of some groups would be small or large. Consider the following, which presents daytime temps. So notice we've got interval, 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 no interval, 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 right? And so we've got a little bit of a misleading thing. And so they want you to find the mean and standard deviation of this group. So let's go ahead and open StatCrunch. And we had a homework problem. This is where we're going to go stat. Let's see here. We want frequency. Oops, I'm sorry. Stat. Summary stats. There we go. Grouped bin data. The bins are in the temperature. The counts are in the frequency. Midpoints defined by the average of the limits. Let's try that one. And let's see here. Hit compute. And there we go. We got a mean of, oh, that tells me right there it has to be the other one. So edit. And we want to do it consecutive lower limits. Consecutive lower limits will determine that. Let's try that now. There we go. So around that. So that's tricky. So if there's one interval that isn't the same, like this one, you're going to want to pick the consecutive lower limits instead of the middle of the interval. That's different. And so that would be 70.8 if you're on the there's 10. Standard deviation would be 3.5. So be wary of that one again. That table, this one right here really messes with us. So when we want to find that one, we're going to want to go summary stats, grouped bin data, temperature, frequency, but use consecutive lower limits for that one. And there we got it. Cool. All right. All right, so it says open the applet to complete these parts. So we'll go ahead and do that. We'll get this little applet, and it allows us to move things around, and it'll help, you know, get it to where we want. So it says click the reset button and create the data sets of 5 observations. So let's see if I can get this. There we go. There we go. 3, roughly, I'm sorry, the mean and the median are roughly 3, and the standard deviation is roughly 5. To add a point, click anywhere and move the point, click on it and drag it. So we can, so if I go bam, put that right, 3 and 3 and 3, okay, and it's going to let me put those right there. Okay, well, that's pretty, I guess it's more of a conceptual question anyway. They want this first one to have a standard deviation of 0.5. So we got to find 5 points. So if we just kind of just mimic this right here, you can see the standard deviation is 1.5. So it's not that one. If we move the points to more like this, standard deviation is 1. So it's not that one either. And if we go over here, that's going to obviously be way too much for us. So it's going to be that one. And let's make it look like that. If we go, those are at, yeah, 3.5. So just move these over a little bit. So you can get this applet open, and it'll actually help you see that. So there you go, 5.5. So that's the right one. So we'll click that, and that is right there. And if we scroll down, part B, roughly 1, so we kind of already made that. So pretty much on this one, you just use that applet, make the graphs, and this is a standard deviation of 0. That's pretty easy because they're all the same. And so let's look at this one. Let's see here. What does the standard deviation change when a 7th observation near 10 is added between 0 and 5, where the mean is roughly 3? That would really increase standard deviation because that would really spread it out. And near 25, again, that's going to be increasing the standard deviation a lot. And what is this? The standard deviation does not resist measure dispersion. So it's kind of like mean. Mean gets pulled hard with one weird data point. So does standard deviation because it takes into account every data point. So I think that's what that's trying to teach you there. Here's another one. Maytag wants to administer a satisfaction survey using the customer. They select 50 customers, randomly select 50 customers. So it's a simple random sample. Systematic is like we pick every like 5th. Convenience is whoever's in front of me. Stratified means we just break it out by geographic or demographic. And clusters like if we sampled everybody like in a neighborhood or something. Okay, I'll keep going here. All right, again, this is a box plot, so we're going to do a show work on this one. Oh, and let's see here. So it's well documented that active maternal smoking during pregnancy is lower birth weights. Research will determine the relationship between the two. So if we just go ahead and open that, so we got smokers and non-smokers. We open this in StatCrunch, and this is an observational study. Do that. We'll get here. I'll close that. All right. So it's an observational study that did not change. They didn't tell people to smoke with their babies. Explanatory variable is whether or not the father smoked. The response variable is birth weight, so it's like secondhand smoke. Lurking variables that might apply. Obviously, the eating habits and exercise habits, all the things that the mother may have done to affect. So it looks like they had chosen. It could be eating habits, exercise habits, and I guess the father's weight, no, and stopping habits, no. Whether or not the mother received prenatal care, those could all affect the birth weight of the child. There's going to be other lurking variables. Stated the birth weights were adjusted for possible confounders. What's that mean? It tried to say if there's other variables like these. So like if they took all the babies that were their smokers, but they also had premarital, or they had exercise, right? So they try to control these other variables to see if the smoking was really what was causing the difference. Okay. Attempt to adjust the results that may have also related to birth weight. So if they found that these other things were affecting it, then they maybe didn't look at those. And then they wanted the mean, median, standard deviation in the quartiles for smokers and non-smokers. And so that would we can just actually do both stats, summary stats, columns, and you can go click and then control click. So you got both and hit compute, and it'll put them side by side. So you can fill in all of that relevant information there. And then the side by side box plot. Let's try that. I don't know if StatCrunch will do that. We'll find out. Graph. Let's see here. Box plot. Boom. And boom. And let's do it horizontally and compute. There it is. Yeah, that'll do it. Duh. All right, so then you can see which one matches. Looks like, there we go. So the smokers looks like they had lower birth weight. You can kind of see that the median's here. So which of these graphs is that? And this is a show work, so you want to take a screenshot of that and then upload this one as well. And it looks like it's definitely that one. Cool. All right. And that confirms. If I look at that data, it definitely looks like these babies have lower birth weights with the secondhand smoke from the fathers. That's a good question. It says, why does the median resistant, but the mean is not? The mean is not resistant because if it's skewed, like I said, if there's one that's really weird, it pulls the mean, but it would potentially not move the median at all, or at most one position in the counting. So the mean is not resistant, and it also says the median is resistant because the value that lies in the middle of the data when arranged in ascending order does not depend on the extreme. So this, even if there's one really weird, it won't affect the median very much. So just kind of stating the obvious there. All right, this is going to be a show work again on this one. Looks like they want us to make a pie graph, right? So if we go ahead and open, let's see here, open in StatCrunch. Now let's do this again over here. And do that. All right. And they want, would it make sense to draw a pie chart for the land area? Yeah, because it would show, oops, how they can, yep. So pie graph is when you're trying to show how does one part compare to another part, or how does one part compare to the whole, excuse me. A pie chart is good for part to whole. Bar graph is comparing part to part. And then they want you to actually make one. And they want to make it for which one? It's land area, right? Makes sense. Yeah, land area. So we can show graph, pie chart, let's see here, with summary, I believe is what we want. The categories are in state, and then we want to do the counts in the land area. And let's do that. There we go. So it looks like it's looking most like which one? Would it make sense to draw a pie chart from the highest elevation? No, because that's when you're trying to compare a part to another part. That would be better with a bar graph. So no, it doesn't make sense for that elevation. Cool. If we look at that data, again, we're trying to say, out of all these states, how does this state compare to the group pie chart? Highest elevation, that's not really a thing where we're comparing. It's not like there's a whole to compare it to, but each individual things, and we like to compare it to each other. So a bar graph would be better for that one. The town's January high temperature was 38 degrees Fahrenheit, standard deviation of 8 degrees, while in July the mean was 77, standard deviation of 8. In which month is it more unusual to have a temperature with a high temperature of 56? So this is like a z-score calculation. And I'll just kind of do that really quick. We'll just do it on Google here. Remember, we could take 56. So 56 minus the mean. Let's see if I can find that again. Let's go. Not there. Not there. Not there. There we go. There we go. So we got 56 compared to 38, and 56 divided by 77 compared to 77. The fact that it has the same standard deviation makes it a little bit of a no-brainer. Essentially, it's which one's further away from 56. So 38 and 56, but I'm going to do this even if we'd had different standard deviations, because I think that would be a more interesting problem that they would give you. So I just want to get that 38 and 77. So let's look at that. So if I go 56 minus 38, that's 18. And then if we divide that by 8, since our z-score is 2.25 standard deviations above the mean. So that's significantly above. And the other one was what again? 77. So we do the exact same calculation, but we go 56 minus the mean of 77. That's negative 2.625. So that's actually more extreme. So whichever one has a larger z-score is an absolute value of it. So that's where they get where, yeah, they want you, oh, there they go. Yeah, they want the standard deviations right there. So 2.625 is in the July, and 2.25 is for the other one. Remember, it's kind of interesting here that they didn't care about if it was positive or negative. So there's counting. They're like counting how many, and when you count is what is positive. So that's why that's 2.625 instead of negative 2.625. So it's a z-score calculation one. Okay, a study that requires individuals to look back in time, that's retrospective. You had that one. And these are pools that come up more often. I think we've had this one as well. Non-sampling versus sampling. This one. Control variable. All right, here we go. Weight of an organ in adult males is bell shaped, so it's normal distribution. They give you a mean of 330, standard deviation of 45, and it says use the empirical rule. Again, the empirical rule is 1 standard deviation is 68% of the data, 2 standard deviations is 95, 3 standard deviations is 99.7. So it says about 95% of the organs will be between what? That's 2 standard deviations, so that'd be 90. So if I go 90 above and 90 below, that would be 240 and 420. So it's 2 standard deviations both ways. It says what percentage are between 285 and 375. That's going to be 1 standard deviation above, because 45 on top of that, 45 from that. So that's the 68 rule. And then how many are between 285? Yeah, C is between 285 and 375. It says with less than that. Okay, so let's see here. If you draw a normal distribution, and 68% is the middle, what's left? 32%, because that's on the outside, less than or greater than. So 100% minus 68% is 32%. And the last one, what percent are between 195 and 375? So again, that would be a little bit of a tricky one. In fact, I'm going to pause this so I can get some whiteboard to write on. All right, so I pulled this up so I can kind of draw this out. So let's do this normal distribution. And what they're asking on this one was 195 and 375. So 195, and 375. In the middle was what, 330? And the standard deviation was 45. So should draw it a little bit more this way. So it's only 1 standard deviation this way, 1 standard deviation this way, and then this way is what? That's 135. So that's 3 standard deviations that way. So it's essentially negative 3 standard deviations. So if we go here, this part, if we go 3 standard deviations, it's 99.7. So essentially that's like 0.15% outside of here. So pretty much that's almost 50%, and that is going to be half of 68, so that's 34%. So if you go 50% and 34%, that's 84%, except for a little bit out there. So it's going to be like 83.85. Let's see if that's what they have. Yeah, 83.85. That's really tricky. But I think if you draw the picture out, again, I'll draw it again real quick. One standard deviation is 68%. So if you cut that in half, each one of these is 34 each. 34. But then if you know that's 3 standard deviations, there's only 0.15. So this would be 50% plus 34%. So that's 84%. But you don't have that. So the area between those would be just about 84%, 0.15 less than that using empirical rule. So that one will be tricky. Okay. Keep going. Stem and leaf plot. We did this one before. Again, the tricky part here was that one. Be careful right at that. So we already did this one. And which histogram has a higher standard deviation? You can kind of tell almost by looking at the scale. Notice these are going by 5s and these are going by 2s. So that's probably going to have a higher standard deviation just because of the scale. There's going to be so histogram A higher because the distribution has more dispersion. And just by looking at it, you would see that unless you look at the scale, it would be more spread out. I guess you go always goes to 30 and 75 too. That helps. But yeah, looking at the scale between the dots would be helpful on that one. Determine whether the zip code is, you'd think it'd be quantitative, but it's really qualitative because it's describing an area, and the number really doesn't mean something, but it's not something you could like find the average zip code or something like that. You can't treat it like it's a qualitative variable, so it's quantitative. That's a tricky one. Quality control manager selects 70 bottles of olive oil that were filled on August 13th. It access the calibration. What is the population? We're trying to take these 70 bottles and infer to the population, which is all the bottles that were produced that day. And what's the sample? It's the 70 that were selected. And then we have a set of data here. Sample 8 students who took the online portion exam, compute the mean, median, and mode. And I don't think by default, let's see, let's open these in factor. I don't know by default if it gives you the mode. Again, mode is the one that occurs the most. And since there's no repeats here, that's why it's going to be no mode. The median, you just do stats, summary stats. There you go. Columns, bam, compute. Move this up here. And there we go. There's the mean is 98.06 and the median is 99.15. So I think that's what they wanted. Yep. Go ahead and close the end here. Getting closer. All right, so we've got a graph here, and this is total tax collected by region. And it says, okay, 50 regions. Explain why the graph is misleading. And let's see here. It doesn't, like it's saying, for instance, how much tax is collected by region. Well, these regions maybe have all low tax amounts, but there may be nobody living in there. They may have no tax base. And so that's why this is kind of misleading, because it'll say, oh, it'd be like Iowa doesn't pay any tax compared to New York. Well, duh, because there's only 3 million people here and there's like 30 million people there. So they should probably be collecting 10 times as much tax. So I guess that's why it's misleading, because it doesn't take into account the size of each region. Okay, and this one, they wanted a relative frequency, and they give you a table. So let's open that in StatCrunch. Again, this is a show work problem again, it looks like, potential. And if we can do a relative frequency, so there we go, stat, tables, frequency, bar 1, and then by default it has frequency and relative frequency. So let's just go ahead and do that. Compute. So there you go. There's your relative frequencies, and they may want cumulative relative frequency, and that might be what they want here. What percentage of the households in the survey have exactly 3 televisions? Oh, it's right there, 22.5%. But yeah, cumulative relative frequency means it just adds all the previous as we go. And oh, there's a graph here too. Constructive frequency histogram. So we could go back to StatCrunch here and kind of look at it, but we could actually just make it histogram too. Graph, histogram, bar 1. Find it. There we go. And that kind of gives us a distribution. There shouldn't be any gaps, but I guess we can deal with what they gave us here. So looks like it was that one right there. Use counts and go with it. And relative frequency is going to look exactly the same because it's the same percentages in each category. So frequency and relative frequency looking identical. And they describe this distribution as skewed right. It's not, obviously not quite symmetric. There's a few high TV households, so that pulls the average up a little bit. So it's a little skewed to the right. And let's see here. Second last one. Random sample of 100 adults, age 18 years or older, was their favorite ice cream. So there's all their selections. What would be the best? So we want to say, how does chocolate compare to everybody, right? So that's a pie chart. If I was only curious about how does chocolate compare to strawberry and strawberry to vanilla, then a bar chart would be better. But if you want to say what's the kind of overall comparison, a pie chart is better. And several neurosurgeons want to determine whether dynamic system reduced the number of acute post-operative delays in the hospital using a static system. The table shows the neurosurgeons collected. So if you see the data, and it wants us to do a dot plot, I think, of the two. So we open that, open StatCrunch. I think we can do a side-by-side dot plot here. Let's try that. Graph, dot plot, and we pick both. Control, click on both, and hit compute. And there, it kind of gives it side-by-side. And move that over a little bit. I'm trying to snap it to the half. Well, it's not like it. There we go. Okay. And I picked C here because I'm guessing that looks the same. Might as well move that to the half too. There we go. Oops. Okay. So you can kind of see how they're stacked right next to each other. So yeah, StatCrunch does a nice job there. Then it says interpret it. It says the number of acute postoperative days is typically less with the dynamic system than with the other. Also, status produces more variation. So obviously this has more spread, and the average would be higher. So this is less spread and it's lower. The dynamic is lower number of days. So. All right, I think that's all of them on this version of the test. I think. Let's see here. Yeah. So I think I've done all these. So this is a video that we can do, and I can do some more of these as well. But hopefully this gives you a flavor, or maybe you're going to experience much of these on your practice exams as well, and this might help you get through them.